one row of the one.
Yes, each row is a transition matrix. And then I'm going to take this and the finite case is exactly this matrix multiplied by h. H is a function on a finite state space. So like h will have a value, h is 0. H of, oh, sorry, we don't like that one. H of 2 and h of 3. If I plotted this function, I have 3 values I can take on. Maybe it has a value here, a value there. I don't know, it could go negative maybe. Our goal is to figure out this function. It is a vector and a function, it's just over finite. So what we're saying is that this, too tall? Oh, you're right, because it needs to be 3, sorry. Yeah. I'm used to matching up square matrices. Okay, so basically it's just going to be h of 1, h of 2, h of 3. Okay, we're calling this state, the state we move to x prime. It's still just a member of our state space, but we're moving to it. So we call these x prime, and you can see that they're also showing up here. Okay, so when he says the sum over each like x prime, he's saying, so we're going to take this element. This is p of x comma 1, and this is p of x comma 2. Where I'm using for my specific choice of x, the thing we're starting from is that. And so for that specific x, I'm going to do this, 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 and then I get the result like h of x. But that was really, this was really what like starting from here, you know.
I don't know. X, it's pu h of x.
Yeah, you're right. Sorry, not h. Yeah, correct. This is what he wrote there. This is going to be the sum over x primes of p, and now not just any starting, we're specifically just this row. So this is the one where the thing we're starting from, for lack of better notation, was like the 1-1 choice going to
P1, put 1 in the subscript.
Oh, that's what the U is for. 1, 1. Thank you. Comma
x prime, so it can be k, yeah, call it k, and sum it over all k.
Well,
no, I think this is confusing.
Okay. Yeah, it is. At this point, I know what I'm trying to say, but I don't know how to say it.
Yeah, just make it x prime. Just write the equation.
Yeah, well, then I was going to write it as like each individual row multiplication.
Right. Yeah.
So just write over x prime.
Yeah,
and then this is the sum over x prime.
Yeah. I remember times h of x prime.
Times h of 1.
No,
h
of x prime.
Yeah, gosh, sorry.
Yeah. That will give you a 3-dimensional.
And then you have that expression
this,
for each
and then
row.
yeah, we do the same thing again. X prime, p. Oh gosh, there's going to be a lot. Yeah.
It's just for another u. So
yeah,
you'll get two.
So is there 2 sums?
Elements of 3 dimensions.
Right, so that's for a specific u and a specific x.
We're going to get as many rows as there are here. So this is going to be as tall as n by m. And we're going to have 1 for this choice, 1, 1. The same thing again for the choice 1, 2, and the same thing again for the choice 2, 1, and all.
I think the key is that this is a scalar value, and you can interpret it as a row times a column vector.
Yes.
That's a scalar value.
And that's the value. That's the value we get here.
Yeah. So this will give you a 3-dimensional.
I don't think we want to go to 3.
This is.
No, don't do that.
This is 3 cross 1.
I think it's a
and you
much
get for
simpler
another
question than
u.
you're making.
It's just this is just the value. This is just the value.
For this specific one,
Yeah,
it's
this
just
is a
a
vector.
6-dimensional thing?
No, that's a scalar. The circle is a scalar.
There is summed over x prime for a specific x, right? And this is for a specific u.
Like it's just an n by m. It's like an n times m by n multiplied by n by 1.
there's two ways to think about it. Let's not mix them. You know what I mean?
Okay, yeah.
So this is, both views are correct. So this is correct. It says NM top by N matrix.
Yeah.
In this case, M equals 2 and N equals 3.
Yeah, so we have six.
Yeah, finally get 6
It's
elements.
also
That's- yeah.
correct to call it cube.
Yeah, instead of stacking these, we could have also chosen all possible U's to go into the board, and then had a cube and a tensor product.
The way this is written, yeah, the output is a 6-dimensional vector. I just wanted to keep that.
Yeah, 6-dimensional thing.
Yeah. By leaving the output as a 6-dimensional vector, just like before we had h of x was like that, or now we have like this pu h of x. I think you meant to say three-dimensional in our case.
6, because U could be 0, 1.
Yeah, but like the resulting. Oh, you're right. No, never mind. Yeah, 6, 6, 6. Okay, yeah. It was just 6.
So with the
all I
same
meant
thing-
was that if you have P of 1, let's say 1 is U equal to 1, X, sorry, P of P1 H of X, right? And X can take values 1, 2, and 3. So that gives you a 3 cross 1 vector, and you will have P2 of,
I'm not agree, that's confusing.
okay.
P1H of X is a scalar.
Yeah, okay. I mean, this will be 1, yeah, and then you have P1 H of 2 and P1 H of 3, and similarly P2 H of 1, 2, and 3. Yeah. I mean, you can do it just as a matrix vector multiplication, then this, yeah, I mean, if you take H as a vector, then you get a 3 cross 1 and 3 cross 1. So all 6 can be solved in 2 steps. That's all that I know. That's all that I know.
I think the key is that's a scalar. I think that was what was confusing.
Yeah.
That it's a scalar value. I think, is that?
Yeah. For a given X, it's scalar.
No, but I think that's what's causing the confusion.
Yeah.
Okay. But yeah, so in this formulation, the pair X and U
Or it
were
shows.
labels for the rows.
Yeah.
You know, and so the first row is the pair 1, 1, the next is 1, 2, and so forth. Yeah, and that's one way to code things out. And you can see how this is one complication of coding is how you represent this data. Yeah. So yep.
So for each, looking at the value iteration policy, for each value of x in the minimization process, you're going to have, or in the case of the homework problem, you will have 2 U's, so you're picking the.
Yeah, in the homework it says, do I drive or don't drive? And you look at it, there's going to be only 2 actions.
Okay, but in any generalized problem, essentially, you would look at an x and all possible U's and pick the one that is still finite. Right? Okay.
Yeah,
This
so
is
you're
together,
gonna use finite
you
also.
minimize between U equals 0, 1, 2.
And that's what guarantees that the size of Bn plus 1 is the same as Bn x, right?
Yeah.
The minimum U.
Because you take the minimum here. Exactly.
So yes, for very small state spaces, I can imagine just going through all possible options and picking the best one. If my state space or input space had, say, 1,000, what's like the Schonlein certified way to find that minimum
Yeah.
efficiently?
Oh, we'll get to that. So we're going to get into all kinds of crazy ways to make this problem, to approximate it. We'll get into that.
Root 4 is exhaustive search.
Yeah, that's all.
Regardless of size.
So we're going to get into approximations, and we'll design them so it's easy to design. You know, okay. Just, so one comment on value iteration, and then we'll leave it. Just a fun fact. I need notation first of all. Let's define phi n of x to be the minimizer. so there's that. And let's define Cn of x to be equal to C of x comma phi n of x. Why would I do that? Because that's a policy I might apply. Oh. And if I apply this policy, well, that's my cost function. If I decide, to take that as my policy, so my input is just that function of the state, well, then I get a cost function that's just that function of the state. It all becomes that. And I might want to evaluate that policy. And how would you evaluate average cost performance of a policy? How do you get a bound to the average cost? There's only one technique you know. Poisson's inequality. So remember that result for value duration before? So we went through value duration without the minimization. The same result holds here. So suppose well,
There should be an extra n on that C, right? On the right-hand side?
no. Remember, my cost is a function of states and actions.
Yes.
All I'm doing is I'm saying I'm choosing my action to be phi n of x.
Oh, okay. I see.
So all I'm doing is I'm plugging in the minimizer.
I got you.
So suppose that for some policy, I'll call it phi bar 0, because it's not going to be this one. Hold on. I'm going to have to give this a name as well. I'm going to have notation, sorry. The same notation. So it's a bit weird because I'm just saying, suppose that if there's some policy in the universe for which I have an inequality like this. And so the idea is a finite state space, of course, I mean, I could always take this big enough so it's true, but the point is that suppose I have this and it's really small, right? Then it turns out this is true for every policy.
Sorry, what is small?
In practice, I'm going to try to get a really good initial condition. So I'm going to try to find a V0 so that for some policy, that's really small, Okay? And then basically there's a sequence of decreasing bounds. I think they're strictly decreasing. I have to check that, but I'm pretty sure they're strictly decreasing. And I'm going to say the same bound holds for every n. And so you all know that means that for the nth policy, my average cost is bounded by eta bar n, and those bounds are decreasing, And so that was what I was saying about, well, all right, anyway, fact, all right? So I get a sequence of policies whose performance satisfies a bound, which is getting smaller and smaller and smaller. Okay. Damn, time flies. I don't know, we're not going to be able to say much about that. What's that?
The fact that it's all derivatives.
Yeah, that's right. No, it's good. We'll survive. Let's call it fun fact number 1. Yep.
And that phi n is the same phi n due to 5?
Yeah,
Okay.
yeah, that's right. So here I'm just saying, suppose that, yeah, so if I have a bound, and of course I should say that's gradient equal to eta bar 0. Yeah, so the bound for my first policy is better than, my original one. And the other thing is, I mean, the fun fact too is much more important. Let's see. One second. Let me write it down, and then we'll talk about it. So MPC, put it down and look it up in Google. It's for some of you who.
Is it model predictive control MPC?
Yep.
Or different MPC?
Model predictive control. So model predictive control. What you do is you solve a finite horizon control problem, you take the first action, and you take that as your policy. Phi n is that solution. Phi n is the policy for model predictive control. It's the definition, okay? Model predictive control, model predictive control. The definition. Now that's not how they do it numerically. What you do is time step, solve a finite horizon control problem of time horizon n for my current state. I end up with this state. Then with this current state, I solve the n-step horizon problem, right? But it's exactly the same as that. It turns out it's state feedback. And people say that we don't know if it's stable or not. Well, yes, you do. If you take your terminals, this is true for general state spaces, anything. If you choose your the penalty function here, that's V0. If you choose V0, so it's a Lyapunov function for some policy, then this state feedback policy is stable. And you've got a bound on its performance. It's at least as good as that crappy policy you used, you had here. So even though you're not applying state feedback when you run MPC, it actually could be interpreted as state feedback, and you have a performance bound, and you have stability guarantees. And that's something, David Main, who sort of popularized the algorithm, did know that, David Main, for the deterministic case, he knew this. In the 60s, probably, 70s or something, David Main, who's my academic grandfather, by the way. So he was the one who really pushed this thing. But it's for some reason it's not commonly understood. So it's so it's something So two fun facts. Yep. Finite horizon. That's what MPC is. MPC, you look at a fixed time horizon. To solve this, you need, you're solving it, for a lot of data here, but you only apply U0, but that's what I called phi n of x0. I'm just thinking of 0. What happens in MPC is that at every time point, you reset the clock, pretend it's 0, go n steps ahead, and then you find the 0th input, and you apply that. You ignore all the other inputs.
Would v sub n equals that? Wouldn't it mean like u sub something, because it's like the argument with respect to u?
This is the argument over all inputs, adapted inputs from 0 to t.
The argument.
No, not argmin. God, it's a min. I'm sorry. I've just been writing that argument. It's a min. It's a min.
Yeah.
Excuse me. I'm sorry. It's a min. The value function. That value function. And when you do this, the you get a feedback law, which is exactly what you get from MPC. It turns out to be identical to MPC. So you get, like I said, performance balance and stability guarantees. You know? So it's something, you know, we asked, what's the good of this outside of a finite state space? There's an example.
So you made a statement I would like to make sure I understand before I believing this is true.
Yeah.
That if you are doing MPC and your value function, you can show like every single time you run your finite horizon, the value function that you get also solves the Lyapunov equation.
No, because MPC, you don't actually compute this. So MPC never does that,
Yeah.
but it very indirectly does that.
Yes.
Yeah.
So like how do I go about claiming to somebody MPC is stable? Like what's the
Just
sentence I
that.
say?
Well, because even though the algorithm you never know that you never compute this, you never see it, but it exists. Because with this policy, you are, this is part of this minimization,
So
right?
you show that the value function that we would get from this specific problem,
Yeah.
this dynamics, always turns out to also be a valid Lyapunov.
Yes, and it does.
Then
As long as you initialize, so this is a Lyapunov function for some policy, this turns out to be a Lyapunov function for this policy because of this right there.
So we're always employing the Lyapunov
So
happy
there's a-
technique over a short window. So
Yeah. Oh no. This is a global Lyapunov function. See, this is our Poisson inequality. So even though we're solving a finite horizon problem, we have infinite horizon performance guarantees and stability. It's really cool. So the whole point of MPC is to avoid this because you are in a infinite. X is uncountably infinite. You can't compute this value function. So what you do is you just, for where the state I'm in now, you compute the optimal sequence of U's. So so you never, ever, ever have this function in MPC, but it's out there and it solves this inequality. So therefore, you know you have a stability guarantee. It's really cool. Yeah.
So we're guaranteed that it always solves one of those?
Well, as long as you initialize, you might know, you might find some stupid policy that you can analyze and find some Lyapunov function for it to prove it's stable. So as long as you can find some policy for which the Poisson inequality holds, then that's true for every one of these functions. So no matter what time horizon you take MPC, you'll always have a stabilizing policy. You don't have to take it really long. Yeah. The only reason for taking it long is to improve performance, and that's sort of clear here too.
Makes me want to say that the claim here is that like MPC is like always stable.
It's always stable as long as you initialize it properly.
Okay.
Yeah.
As long as you initialize the search for the. So again, you don't,
That's
you
the
don't in your code you don't actually find the value function.
No.
It's only if I initialize the value function.
Yeah, as long as it's a terminal cost. As long as you make your terminal, and this is deterministic or stochastic, continuous time or discrete time, nothing matters. As long as your terminal cost satisfies a Poisson inequality there, then you've got stability. And if you had an indeterministic setting, this would probably be 0, and these would all be 0.
So as long as you choose your function v0 of x.
Yeah, that's how if you choose this to be 0, as people typically do, then no, it could be unstable. Because there's no way that you take 0, you're not going to get a...
So your choice for the value function at the end of the finite window, that last x of n,
Yeah.
if that satisfies only Lyapunov of Poisson's inequality, then we know that the solution here, the full Vn, is going to also satisfy a
Yeah. And the proof is identical. I'm not going to give it, if you look at the proof I gave for the fixed policy case, there's no changes whatsoever. It's identical. So it's in those notes that I sent you today, but there's no difference in proof. It's a trivial result. You just write, where is it? You just write Pn, Vn. When you plug in the minimizer, you get Cn plus P Vn Vn equals Vn plus 1, but Vn plus 1 is just Vn plus 1 minus Vn. If you go back and look at the notes, it's just a one-liner almost. It's an incredibly short proof.
So telescopes?
It's by induction. You go back to the previous proof, you'll see by induction you show, it's amazingly simple. All right. So I'm not going to be able to do it, but let's get our brains in the mood for how in the world we think about a Newton-Raphson, all right? Okay? Yeah. All right.
Calculation of discrete derivative.
Okay. No, it just turns out to be a really nice version. I mean, where's our friend again? So I know this looks weird. Okay. So Newton-Raphson, usually when you learn about this, you're given something equals 0, okay? And what you do is it's given at stage n of the algorithm, or n plus 1, I have a hn, you know? And then I go through and I draw a tangent line. There it is. All right. Now these are functions I know, but but the same thing is true. So this maps RD to RD. So instead of a curve, it's something we can't picture it because it's mapping RD to RD. But it turns out you can do this.
And so I missed it. What is T of H?
Oh, remember, T of H was our friend. I was going to remind you. So T of H, evaluate at X was our thing. Yeah. The thing is that it doesn't. We don't want to get lost in the forest right now. We want to. Although maybe it's worthwhile. I'll write it down again. Yeah, no, come on, don't get depressed. Now, why am I drawing a happy face like that?
Because it's convex.
Yeah. Now, why is it convex? Because T is concave. And why is T concave? Yeah, because if this difference was convex, it means that T is concave, right? Now, why on earth would that be true? It's right there. It's an awesome fact about this thing is it's always concave. And I won't have time to prove that algebraically, but concave means a sad face if you graph it. And so for each fixed u, that's a linear function of h. It's just matrix multiplication, right? If I fix u, it's linear. All right? Whenever you take the minimum of linear functions, it becomes concave. And in fact, that's a definition of concave functions. Every concave function is a minimum of linear functions. 0. If and only if. So a function is concave if and only if it is a minimum of linear functions. That's it. And I'll do an algebraic proof as well next time. But that's it. So that's fantastic. That's what justifies this. So, having this structure here where you know, draw it like this is really, that's when Newton-Raphson works, you know. Actually, you don't need concavity, you need increasing, but still, yeah, that's not true. Yeah, so it's when you're trying to find minima. But anyway, you actually want an increasing property, yeah. Because you don't want this thing to come up again. But anyway, forget that. But anyway, there's lots of values of concavity, and one of them is also the fact that yeah, let me say a different way.
Seems like,
Oh, I erased it by mistake. What's that?
I don't know if the way you drew it,
Yeah.
things seem to converge a lot faster.
No, Paulus iteration, well, that's the point of Newton-Raphson. It's blindingly fast. You know, and
Unless you like choosing something on the HM plus 1 and I said one there.
Unless you choose the wrong step size.
no, there's no step size. Oh no, I have to remind you what, you know, you've forgotten real Newton-Raphson.
Well, I know that the traditional algorithm is used like in
No, that's the one I'm talking about. No, that's the only Newton-Raphson in this course.
But if
And
you-
Pluto is a planet.
If you chose that direction,
You'll
it
see.
would show some arbitrary.
No.
size.
This is such a nice problem. You just use a standard Newton-Raphson. And so what do I mean by that? I say that I take a linearization. So you need these linearizations. You need that T of H to be approximated by, as you see there, T of Hn you know, you're basically doing a first order Taylor series expansion. That's all we're talking about. The value of concavity is that we might not have gradients, because this can have corners, but we have subgradients. We have, the problem is that T can have corners. So what happens is that T is actually piecewise linear. What happens is you minimize this over U, really you get a policy. You know, when I go through for each x, I minimize over U, really I'm getting a policy which depends on H. And, you know, we'll see next time, that gives us, it tells us that TH is actually just a linear function of H in some region, and then suddenly the linear function changes, and suddenly it changes again. So again, I don't have time to get into that. But it's piecewise linear, so this plot's not really accurate. It's actually wham, wham, wham. It's hard to draw these things. And so what happens is if I'm unlucky, which could happen, and that's Hn, then there's not a unique derivative. If I take that as the derivative, I'll end up with my Hn plus 1 being there. And if I take that, by God, I've just nailed it. Actually, I didn't. I mean, that's H star, right? Yeah, we want this to be 0, so that this is 0. Yeah. So the piecewise linear property is actually valuable. It's useful. But it's too pretty to rush. But at least we can say that. Oh, but yeah, that's right. So I mean, I will say this. That's right. So here I wrote down a picture of what Newton-Raphson is. You've got this in this case a convex function. I go through, I take its linearization, and then I solve the linearization. And let's make that formal, okay? So I'm going to come up with an approximation. There's a slight technicality because of corners, but it's not a big deal. When's that? Well, do you insist?
Oh, I can wait.
And instead of solving this equals 0, we solve t hat we solve, instead of trying to solve this nonlinear equation, being equal to 0, we take the linearization. Of course, that depends on it as well. Can you put that in? That's going to be a linearization about that point. Maybe that's what you're going to say. And so you plug all of this in.
Finding roots of the linear equation.
Yeah. And I guess we can, shall we do it? Yeah. Yeah, that's right. So it's, but so I guess, but we have to do it, don't we? So it's hn plus 1. We have to solve hn plus 1 minus this, which is t of hn So this is 0 is the same as saying that is 0. Is that, something's wrong there, is that really it? I guess so. It's got to be right? So no, it looks,
Yeah, I think evaluating hn plus 1 might be causing some issue.
no, that's right though.
Is that right?
I take the linearization. Oh wait,
Like you're saying hn plus 1 is the root, so it should be the only thing that shows up if
yeah.
the whole equation is equal to 0.
Well, no, but I mean, I take the linearization and I solve that equal to 0, and I have made a typo here somewhere. That's why you should always look at your notes. I mean, this is the linear approximation, right?
Yeah, and so you just, what you have to the left-hand side of that t hat, like that t of hn plus a sub n, all of that, like your goal is just to make that equal to 0.
Yeah, and that's what I'm doing here. So I plugged in that equals,
Find the h that does that. And then
yeah,
just call it.
when I'm just plugging it in, and for some reason it doesn't look, it looks strange to me. Because I've got the hn plus 1 there by plugging in, and t hat 8n of h. I plug that in, I get t of hn plus an hn plus 1 blah, blah, blah. And does that look right to you?
I agree with everything on the board.
Okay.
I don't know if it necessarily.
It just looks strange to me, that's all. Yeah, I guess so. Yeah. So,
Solve the hn plus 1.
fuck, it just doesn't look right. No, there's a typo somewhere. Isn't there?
Like, why are we setting h minus t hat equal to 0 and not just t hat?
Oh, because I, check it out. Yeah. So I want that to be 0, and so I'm approximating
Yeah,
that by
sorry,
3.
our function that we're trying to minimize wasn't t, it was, or not that.
Yeah.
It wasn't t.
Oh, Jesus Christ. We'll have to... Well, anyway, I've done something strange and I can't figure out what it is. And my notes here aren't helping
My
me.
question might make
Yeah.
the whole thing move.
Oh, okay, yeah.
Is because, so if this is piecewise linear, we don't even really have to linearize per se. We just kind of use that chunk that we're on.
We're going to do that next time. Oh, no, that's a beautiful thing. I mean, there's a formula for this. To rush it would be sad. It's so pretty. There's a formula for this that's so nice. And we'll give it, I'll give it to you next time. Okay? I mean, so that's easy. I mean, see, once we get it, we're solving this equation, but that doesn't look right to me somehow, because it looks like I get a I plus an hn plus 1, but I guess that's right. Yeah, and I guess that is it. You have to solve a linear equation. Yeah. Okay, so you have to, anyway, that's it. So there's no mistake. It's just an implicit equation you have to solve. But notice it's like the Poisson equation we saw before. I've got a matrix times hn plus 1, is related to a matrix. I'm trying to solve, I'm going to write it down, damn it. hn plus 1 so we're going to make sense of this later. That equation is the same as this equation. That is of the flavor that we've had to deal with before, like Poisson's equation. I've got a vector which we're trying to solve for is some vector. This is a vector as well, and then A is some fixed matrix times my vector. It's exactly like Poisson's equation, and then minus another vector. Well, we'll see it is Poisson's equation. When we unravel this, and we find out what A is, this will be Poisson's equation.
Sorry, can we just bring the an times hn plus 1 over to the left?
Yeah, we still have to solve. We could do that, sure.
There is an
Factor out.
No. It doesn't. No, an, hn. Oh, what do you mean?
I'm just saying you could solve for hn plus 1. Yes.
That's all we're trying.
To be implicit in the
No, it's still implicit. I mean, it is. Because, it is. It's implicit because I've got an hn plus 1 and a. I can't invert. We'll find out next time.
Can or can't?
Cannot.
Or A is a matrix.
A is a matrix.
But
In the scalar case, you can.
Okay, yeah.
If it was all scalar, I could just.
The inversion part is the part because you can always just factor out the hn plus 1 and just put an identity matrix there. It's like b by.
It's true.
yes.
Well, we could. Well, that looks even more. That looks even more.
Poissonic.
Yeah, Poissonic. Yeah. So hn plus 1. So you're saying take this to the other side, and that's equal to t of hn minus an hn. Cool. You could do that as well. And you'd be very tempted to invert this, but see next time it's not invertible because it turns out this will be, believe it or not, this will unravel itself and become Poisson's equation. And again, I don't want to ruin that. It's too pretty to see. This is not pretty, obviously.
So you tell me it's piecewise linear.
Yeah.
Such that an should be like this nice, like.
It is.
constant
An is
feature.
so elegant and nice.
And yet, can't.
Yeah, that's right. I don't want to rush it. Yeah. It's very easy to see. It comes from. The thing is, you have to know a bit of how to think about subderivatives. A subderivative is a supporting hyperplane, and you have to think about what that means. And so, I'll have to explain to you what I mean by that. But the fact that this is defined as a minimum makes it trivial to find gradients. And once you figure what A is, that's a Poisson equation. So Paul's iteration, you're going to solve a Poisson equation, and then, there's no point in saying more. We'll do it next time.
Why did we jump back to continuous state space.
No, it's not continuous state space.
But like H is taking
No,
values
H,
over all
no, H is a vector. H is continuous. H, see, what looks weird is that I'm pretending H is a scalar when H is really a d-dimensional vector. But H lives in a continuous space.
So that's a functional then, right?
Okay, I see what's going on.
Yeah, that's what's strange. H is a function. H,
No, I'm saying
yeah.
this thing you're drawing right here is a functional, not a function, because it takes it into its
Yeah,
function.
P of H takes, well, you could say it takes vectors to vectors, it takes functions to functions, depending on how you want to, how to think. Yeah,
H is a vector.
yeah, yeah. And so it's just weird to write it as if H is one-dimensional. It never will be. That would be if there's one state. It's unlikely we'll see that.
I have one quick question.
Yeah.
The upside down triangle, what is that? Is that like definition?
Yeah, oh yeah. So going the other direction, usually I'll put a triangle on top saying equal by definition, but I'm saying this is equal to that by definition. That's going backwards.
Is that an actual standard notation? 'Cause I've
Yeah.
never seen that.
Oh, really? No.
Whenever I encounter that, I just do a backwards colon.
Oh, okay. Oh, yeah, that's another way of doing it, yeah. It's to put a colon, yeah. But this is more clear, I think. So that's equal to that by definition.
Right.
Yeah. I think, yeah. Cool. Well, I love the discussion. Awesome. I don't mind being slowed down.
I have to wrap my head around like what that looks like.